So good morning, everybody. My name is Tony Studer. I'm an assistant professor in the Department of Crop Sciences at the University of Illinois at Urbana-Champaign. And I've studied corn for over 20 years. I've been in industry a little bit, academia, research institutes. I've studied corn from its ancient origins in Mexico all the way up to modern hybrids. I've generated and evaluated transgenic events and also tried to isolate corn. And so I'm here today to kind of present a biological perspective and a genetic perspective on this topic. And then also I've accumulated some common practices and best management practices for preventing the GMO contamination of organic corn. So the outline of my talk today is just going to be starting with the basics of corn pollination. And so we have sort of a diverse audience of presenters and also attendees. And so I want to go over the basics. Some of it you may know, some of it you may find surprising. And I think this base knowledge will help us understand why we have certain strategies for avoiding GMO contamination. And then finally, I want to just hint at some of the latest research and breeding efforts that are trying to address contamination issues. You'll see that current strategies are not 100% and they have a lot of caveats, but there is sort of light at the end of the tunnel, including some of the research done at the U of I. And so now let's dive into the basic biology of corn. And so corn is a monoecious plant. And so it has the male and female flowers on two different parts. So we have the male tassel that produces the pollen gamete, and we have the ear, which is the female part of the plant and has the egg. It's kind of unique because only about 5% of flowering plants have this sort of sexual structure. And this difference in the location of the sexual organs actually leads it to be a natural wind pollinator. And this fact comes into play when we talk about how best to manage GMO contamination because of this wind pollinating nature and this break between the tassel and the ear. It's one of the reasons I love corn. It's one of the reasons I hate corn. So it's like this dichotomy that goes on. And so let's start with the male part here in the tassel. So the tassel is the site of where you have pollen production. A tassel can produce anywhere from, I've read, 2 million pollen grains to over 20 million pollen grains. And so really it's a powerhouse of spreading male gametes across a wide area. There's a lot of things that affect pollen viability and therefore how effective it will be at pollinating neighboring corn. And that pollen viability depends on a few factors. First of all, to understand pollen, it has a lifespan. And so a pollen grain is only viable for a few hours. That could be either reduced or lengthened based on some of the conditions I'm going to talk about below. And then time also plays into how long a plant will shed pollen. And so a tassel will shed pollen over the course of a day, and that pollen may be crunched down into a small window if you have rain events or it's extremely hot, or it could sort of stretch out and you could have pollination over the whole day. Temperature greatly affects pollen. If during peak pollination time you get a heat wave, that pollen is not going to be as viable for as long. It may not complete a pollination, and this can lead to poor seed set. Humidity also plays into account. It sort of has the Goldilocks effect. You can be too humid and wet, and that kills the pollen, or you could be too dry, and it makes the pollen non-fertile. And then the last thing I'd like to mention here is the duration of shed that is going to come into play when we talk about isolation. And that's a corn plant itself, if you're thinking about an individual, will usually shed pollen for about 5 to 7 days. But when you're thinking about a corn field as a population, that corn field can actually shed pollen over 10 to 14 days just due to differences in the maturity stage of the corn that's in that field. And so that's almost a 2-week window where you have pollen flying from an individual cornfield. Now let's flip to the female side of the equation. And I'm going to start here with silks. And so each one of the silks travels down the ear shoot to an ovule. And so you need pollination to occur on each silk to get a kernel. So there's a one-to-one correspondence there. If you zoom in on the silk, you'll actually see that there's little hairs called trichomes that line the length of the silk, and that provides a attachment point for the pollen grain. Pollination is actually the term used for the pollen getting onto the silk, and fertilization is the process of the pollen grain actually fertilizing that embryo. And so what has to happen here is you could have a pollen grain attached, which is shown here in this picture, and then a pollen tube will actually grow and has to penetrate into the silk and will grow down the silk to fertilize that kernel. You'll notice that there's many attachment points along a silk, so you could have many pollen grains attached to the same silk. However, it'll only be a single pollen grain that wins the race and fertilizes that embryo. So we've talked about the male and female contribution here. And so this is why even if you grow organic corn, you can have GM contamination. And so if you have pollen that enters the system and fertilizes, you will have a GM contribution from that male pollen grain in the embryo. All of the tissues surrounding that embryo are actually maternal. So they are derived from the plant itself, from the ear. And so that will not have a GM signature, but the embryo itself has the DNA that was transferred by the pollen grain. So that's the basics of pollination. Let's talk a little bit about strategies for avoiding GM contamination. And so I think one of the things people often think about is temporal isolation, or trying to isolate their crop from the neighbor's crop using a different timetable. And this can be done in a couple different ways. It can be done by altering the planting time. And so where you adjust your planting time so that the pollination of the neighboring field will not occur at the same time as the pollination of your field. This can be done via planting time, and it can also be done by selecting a different maturity hybrid. So if you have, I think someone needs to mute, thank you. And so the hybrid selection would allow you to pick a hybrid that is not maturing at the same time as the neighbor's GM field. Temporal isolation is fraught with many problems, and so results are highly variable. And one of the reasons for such a high level of variability is due to the weather. And so if you could predict the weather, maybe you wouldn't be growing crops and being a farmer. You could probably make a lot more money predicting the weather. But it's one of the most variable things. I've lived in Illinois for 6 years now. And just in the time that I've been here, it's really hard to say what a normal year is. I've witnessed the hottest summer, the wettest spring, the latest planting date for corn. And so you get sort of this wide range of environmental effects that impact your timing of planting and then also the growth of your crop. One of the things I'd like to point out that people may not realize or think about with temporal isolation is there's a big difference between planting date and emergence date. And so when the seed goes in the ground, if it has moisture available to it and the soil temperature is right, you can get emergence in about 3 to 5 days. And so it can be very reliable. Seed goes in the ground, seed emerges. However, there are factors that can affect that emergence rate. So if you plant into dry soil and you're anticipating that rain and that rain event doesn't come, that seed could just sit into the ground until it's activated by the moisture. And so I've had corn sit in the ground anywhere from 3 to 4 weeks after planting, and it just doesn't do anything until the conditions are right for it to emerge. And so if you're planning on doing temporal isolation, you're probably going to want to go off the emergence date of your neighbor's crop. Pay attention to when the planter goes through, but also look when that emerges, because that emergence time is going to be critical, because that's sort of the starting point for development, not necessarily when the seed goes in the ground. Oftentimes you'll see that hybrids are rated based on maturity, and that's by days. And so calendar days are really ineffective for predicting the biology or the timing of the biology of a crop. And so really what is important is the amount of heat the crop is getting. And so there are other units to estimate maturity called growing degree days. These can be are a lot more accurate in predicting the timing of events. And just to get at my point of emergence, there's a standard calculation of adding 100 to 120 growing degree days for emergence if your seed lot. Some companies put the maturity dates of hybrids based on planting, and some put them based on emergence. So you'd want to check that, and if it's based on planting, you should add 100 to 120 growing degree days, just so that you account for that time it sits in the ground. Soil temperature plays a big role in the planting versus emergent equation. And really, the soil temperature has the greatest effect on the first few days of the life cycle, because the corn plant is closer to the ground and that temperature than it is the actual air. The other thing that I'd like to point out, and I have a couple of tools in the resource section at the end of my talk where you can look at growing degree days for different hybrids in your area. It's a multi-state tool, so it's not just for Illinois. It covers quite a bit of the corn growing region. And then I have another tool where you can look to see how to adjust the maturity date for late planting. So if you plant really late, the corn will actually adjust its own reproductive time. It'll crunch it down a little bit to try to fit in that window. And so there's a calculator for the time after May 1st that you plant and how that may adjust your maturity rate. Okay, so the next thing I want to talk about is isolation by distance. One of the main factors here that you should consider if you can't plant up against a wheat field like in this picture is prevailing wind direction. And so because it's a wind pollinating crop, the prevailing wind will push that pollen farther into your field. If you look at what is recommended for isolation distances, the USDA minimum separation distance for regulated articles is 660 feet or 200 meters. And this is sort of a distance that I've worked with before. This is also the distance used by the Association for Official Seed Certifying Agencies as far as an isolation distance when looking at organics and GM crop distances. However, 200 meters is a really long ways, and I know not everyone has that much space in between the neighbor's field and theirs. And so let's look a little bit at the data on what the distance actually practically is. So here's a table of a combination of over a dozen studies that have looked at percent pollen contamination from a neighboring field and then how close that pollen source is. And so I've highlighted a column over here. So at about 50 to 100 meters, you're seeing consistently less than 1% contamination from the neighboring field. If you drop down to 25 to 50 meters, you can see you have quite a bit more variability, but it generally is under 1% contamination. And so 150 feet to about 300 feet would give you these sorts of results for pollen contamination. And then the USDA measurement obviously is trying to get no pollen contamination. And so it's over 200, it's about 200 meters. So you can see that's actually off the scale of what was tested here, just because the rate of contamination would be so very low at that distance. Now, that's not to say a pollen grain can't travel farther than that. I've learned to never underestimate the power of the wind, and people report pollen grains traveling over a mile. But that would be relatively rare. And so when thinking about a population or an overall grain sample, that would contribute very little to your pollen contamination. The next thing I want to talk about is border rows. There's less specifics on border rows and how to work with those. I've seen general recommendations of having 8 to 16 border rows to prevent internal contamination of your field. But that again depends on how far you are separated from that other field. Think about it, 16 rows at 30-inch spacing is still only 40 feet. And so the border row is going to help by flooding the crop on the inside with pollen that's not GM. It also provides a little bit of a break, but still 16 feet and only, 16 rows and only 40 feet is still not going to prevent all contamination from a field planted directly adjacent. The other thing I'd like to quickly point out is you also have to think about where contamination is coming from. And so I've been talking so far about outside contamination. And so if you think about this as your field and you have prevailing winds from this direction, you will find contamination, but each pollen grain is going to add sort of 1 point of contamination. So a pollen grain fertilizes a kernel. Say you've got a 300 kernel ear, so you need 3 kernels to hit a point, to hit a 1% contamination rate. However, if you've got escapes from your seed. So if your seed is contaminated that you plant with transgenics, each one of those plants is going to produce an ear that's 300 kernels that are contaminated. And then they're going to have a zone of contamination around them. And so you can see that having contamination in your seed lot is a really large source of contamination, and maybe much more so than what you would get due to pollen drift. So that's something I want people to consider, and some of the other speakers might talk about this a little bit more later. So what's the right way? It really depends on your farm. It depends on your situation, what you're planting, what your neighbor's planting. I think you should consider all of these factors, and hopefully the biology gives you some context in making that correct choice. One of the last things I want to touch on and highlight is that there is research looking at addressing this specifically. One of my colleagues at the University of Illinois, Dr. Martin Bone, breeds corn for organic systems, and recently received a grant from the USDA Organic Agricultural Research and Extension Initiative, where they're looking with scientists from Iowa State and USDA in ways of breeding better organic corn hybrids, and then also incorporating a pollen isolation system. And so this is really the thing that gets me excited as a geneticist. There are things called Grammatophytic factors, and you probably haven't heard of these, but they were first identified in 1902. But if you grow popcorn, you've probably used these. And so one of the wonderful things about popcorn is it has this gametophytic system. And so its pollen can pollinate dent corn, but dent corn pollen can't pollinate popcorn. And so this preserves the structure of the popcorn kernel and allows it to pop. And there is zero contamination of the dent corn into a popcorn field. And the way this works is under a normal situation, you have pollen grain that has a pollen tube that grows down the silk. And so that's what fertilizes. But if you have this gametophytic factor, this is a dent corn pollen on a popcorn silk, you have erratic growth of the pollen tube, and this never actually makes it into fertilize the embryo. And so people are working in this project to move this pollen barrier system into organic corn so that it could not be pollinated by GM dent corn. I think that this is something that you should look at towards the future. There is a company now that has a version of this system in their corn, which I'll talk about in the very last slide, which is next. But I think you should also look at this from a policy standpoint. So there's a lot of talk right now about if there's a big push to move this into organic system, maybe legislation that would prevent big seed companies from using this in GM dent corn. And so it's just something to keep, if you're passionate about this topic and GM contamination, it will be something for you to keep an eye on in the near future. So finally, that's all I have to say. I have a list of resources here. There's a couple really good tools. If you want to shoot a question to me in the chat, I'm happy to post some of these links in the chat for the GDD tool, hybrid maturity. Blue River Organic Seed is that one that produces the pure maize that has a version of that system in it. And with that, I'll take any questions, or we can move on to the next speaker.
Well, thanks very much, Tony. If anyone has any questions, I'd love to see it in the chat. I guess I would be curious, Tony, if you've had contact with actual farmers who have been frustrated with GMO contamination, who have sort of shared their stories, and anything that's kind of stood out to you about them.
I sort of reached out to some of the extension professionals in the state. A lot of the questions that they get aren't to do with organic corn systems. I have a feeling that it's not sort of their normal clientele, but I think that if people have questions, that I encourage them to reach out to the university, to the extension agents, because the more we hear that this is a source of interest, I think the more we can compile research and give presentations on best practices.
Okay. I guess the other question I have was in terms of that breeding research and development that's being done. Does popcorn breeding with other types of corn, is that a challenging thing to do, or is that fairly easy? Or
so one of the main breakthroughs that they've had recently is they've identified the source of this gametophytic factor. And what they can do then is they can actually create a marker. So if you know in the genome where that important piece is, you can actually track that as you breed it into different
Mm.
corn background. And so just knowing what causes that effect and where it's located will greatly, I mean, save many years of breeding to try to
Oh,
move that system over. And not only that, with hybrid corn breeding, you're developing new hybrids all the time, and
yep.
so it's not practical without knowing exactly where that is in the genome to keep it in elite material. And so knowing where it is going to keep it in elite material so that organic farmers won't be growing the same thing they grew 10 years ago just because it's the only thing that has it, but it will keep them current with the germplasm.
Got it. We do have one comment from Mark saying it would be a good reference to have a list of non-GMO buyers and facilities to help farmers find the closest to them. Maybe that's something we can send out with everyone's help later in an email to everyone who registered. But with that, Tony, I think we're good. Thank you so much. Really appreciate the background. Actually, we do have one question from Vimbai. Hello, if we use gametophytes in organic corn, will we now not be producing a transgenic form of corn, therefore GMO? Does that make any sense, Tony?
I mean, I could try to take that. So the gametophytic factor is naturally occurring, and so it exists mostly in popcorn germplasm, and so it is not a it's not a transgene. It's not modified from any kind of standpoint of genome editing or anything, and so that's a naturally occurring system that occurs in corn, and it's moved into germplasm through traditional breeding practices. And so having that gametophytic factor in the background of organic corn does not make it a GM product.
Excellent. That's super helpful. I was a little curious about that myself. Great. Again, Tony, thank you so much. This was super helpful. Great framework for the conversation today.